Hi, I'm Barbara Fox, and I did a presentation on computer networks for some high school students. And I thought I'd record it and put it up on YouTube. So this is really computer networks for non-computer networking people. So how many computer networks do you think you use? One, three, or five or more? So we'll come back to this at the end of the presentation. So the first computer network in use was the telephone network. And if you were at your house, the telephone was usually connected to the wall and you would talk and the connection would go over the telephone lines. Now, I grew up in Rhode Island, and if you were making up a phone call, that was really that you were bringing up a circuit. You were going to talk to someone. In Rhode Island, the area code is 401. And when you dialed a number, there would be a country code. So in this case, a country code of 1 is the USA or Canada. There's an area code, which in this case is Rhode Island. Then there's an exchange, and the exchange is the computer that all the houses are connected to. And then there's a house number. So in this case, we lived in Cranston, and if my mom wanted to call my Aunt Susan, her house was connected to a particular port on this computer, and my Aunt Susan's was connected to another port. So my mom would dial my Aunt Susan's number, and the two ports would get connected, and then my Aunt Susan would answer the phone, and my mom would hear her, and a circuit would be set up. And all of the resources required for their conversation were in use, whether or not they were speaking or whether or not they were talking at a mile a minute. They're using the same amount of resources in the telephone network. Now, say my Aunt Rose lived in North Providence, and say she wanted to talk to my Aunt Susan. She's in a different exchange. Her house is connected to this computer over here. So when she dials the number, the computer says, oh, that house is not on my exchange. So I'm going to connect to the computer that accesses that house, and that connection will go over the phone line, come to this computer, and see that, oh, Susan's talking to Mom, so that circuit's in use, so I would send back a busy signal. So say my Aunt Susan hung up and my Aunt Rose called her again, she would dial the number, it would go over the computer network, my Aunt Susan would answer, and a circuit would be made, and then they could talk until they hung up. So say my mom wanted to call her mom in Ireland. She's got to get across the Atlantic Ocean. So she can either talk to her over a satellite network, or more likely she would talk to her over an undersea cable network. And so when she dialed her mom, the cable probably didn't go from Rhode Island to Ireland. It probably went from New York to England, and then there was another cable from England to Ireland. So when my mom dialed her mom, she would dial the number, it would get routed to New York, it would go over the undersea cable to England, then it would go to Ireland, and then if her mom answered, the call would be connected and the circuit would be set up, and then they could talk. Now, there were ships that basically just sailed back and forth, dropping undersea telephone cable so that these connections can be made. So if you look at submarinecablemap.com, you can see where all the undersea cables are, and they're all over the place. There's a lot. You can see where there are a ton of them. It's pretty cool. So when we build networks, we think about two things other than getting them to work. We think about scale and we think about resiliency. So resiliency is being able to send traffic from the source to the destination, regardless of whether or not there are problems in the network. So just like if you were driving from your house to your friend's house, you would drive over roads, and there might be an accident on the road, or they might be doing road work on the road, or there might be lots of cars on the road. And so we need to figure out the best way for you to get from your house to your friend's house. And maybe it would be by taking a different road, or maybe you would go slowly down the road you were going on. But you need to be able to get from where you're going to where you are to where you're going, and that's resiliency. Being able to do your job regardless of any problems in the network. The second thing that we worry about is scale. And scale is how many services can we support at one time? So how many connections can we support? How many people can access the network? How many uh, connections to the Netflix server can you support at one time? And that's scale. So the telephone engineers wanted to build the telephone network to scale for whatever day they thought would be the busiest day for people using the phone. So what day do you think that is? Christmas, Thanksgiving, Mother's Day, or Super Bowl Sunday? Which day do you think the most phone calls are made? So the answer is Mother's Day, because Christmas and Thanksgiving, you're probably home. Super Bowl, you're out with your friends. But Mother's Day, you might not be home, but you always want to call your mom and say Happy Mother's Day. So when the telephone engineers created the telephone network, they created it to be able to support the number of calls they thought would be made on Mother's Day. So at the same time, we had computers and terminals, mainframe computers. When new technology comes out, we usually centralize all the brains in one place while we figure out how to get it to working well. So it's the same thing with computers. We had mainframe computers and multiple people could connect to the computer on a terminal. And if two people were on the computer at the same time, they could talk to each other. But if they weren't on at the same time, they couldn't talk. So these were the first computers, and these are some of the old terminals. Pretty funny. These are tape drives too, the way we used to back up information. And you guys see this today with your game controllers, right? When games first came out, there were consoles, and you could only use a console with controllers connected to it, or controllers that were in the same room as it. So you could only play someone who was in the same room as you. So here we have like Wii bowling. And so we've got the console here, and then each kid's got a controller to be able to bowl. And if you only had two controllers, then only two kids could play, and the third kid would have to watch. But what we wanted to be able to do was play games over the network, and now we can do that, right? You can play at your house, but you can be playing a person at their house, and you've each got your own computer. So people wanted their own computers because they didn't want to share resources with other people, and they wanted to be able to communicate with people on other computers. So the next thing that we had were mini computers. And so it was like everyone had their own little computer, and all of the computers were connected together on a local area network. All the computers were in the same place, and so they were a local area network. And the reason that they had to be connected is, say you came in one day and you wanted to use the computer, and you sat down and used this computer, but you didn't finish all your work. You save your work on this computer, but the next day you come in and someone's sitting on that computer, so you have to sit at this computer. You still need to be able to access your data that's on this computer. So all of these computers had to be connected together. So Ethernet was created. That's the protocol that connected these computers together. And so computers act like people do, right? When they have something to say, they just talk. And if two computers talk at the same time, they do the same thing that people do. They both stop talking. And then one of them will start to talk again, and they'll probably get to talk, and then the other computer will talk, just the way that people do. So it's called collision detection. When the two computers notice that they're both talking at the same time, they back off and start talking. And that works fine when there's not really all that many computers on the network. If you might have one computer that just won't stop talking, right? It's taking up all the bandwidth, just talks. Then the other computers don't get to talk, and that's a problem. So what we wanted to do was make it more fair, and so we created Ethernet switches. So instead of having all the computers on the same wire, they all connected to the same switch. And then if you wanted to talk from this computer to that computer, you would talk through the Ethernet switch. This switch would move the data from where it came from to where it was going. So all of these links are probably running at the same speed. So say all 5 of these computers wanted to talk to this computer's link would get overwhelmed with traffic. We're going to talk about what we do with that in that case in a few slides. So this was good for computers that were in the same area, but what about computers that were far apart, computers that had to be connected by the telephone lines? We call the network that connects computers that are far apart the wide area network, or the WAN. So when do you think WAN networks started communicating? 1939, 1956, 1969, or 1983? So if you picked 1969, you were right. A computer at UCLA had a student on it, Charlie Klein, and he connected to a computer at Stanford Research, and he started to type login, L-O-G-I-N. But the computer at Stanford Research crashed after it received LO. So we had the first computer connection made, but we also had the first crash right away. And they fixed it. They fixed the computer at Stanford, and they were able to connect and send the whole login like an hour and a half later. So the first major network in the United States was called Arpanet. And this network had the US government, universities, and computer companies connected to it. It connected to each other over phone lines and microwave lines and satellite lines. So I worked at BBN, so that was a computer company. Harvard's on here. We've got Los Alamos, Sandia, Stanford. So all these computers are connected together. We also had satellite lines to Frankfurt, where there was an Army base. We had satellite line to Hawaii, satellite line to Korea. So this was the first major network, and this is the map from 1984. And this is the same computer network that had the first connection in 1969, which was Stanford and UCLA. UCLA must be here somewhere. Oh, here it is, UCLA. So how do computers talk to each other over the phone lines? So first of all, the phone lines, if you have a phone line, a DS0 is how much of the telephone line is required to have a phone call. And so that would be the smallest connection that you could have. And that would be 64 kilobits per second. We're going to talk about relative link speeds. So we'll think of 64 kilobits per second as sending 64 cars down the road in a minute, say. Then we had DS1s, and a DS1 was 24 DS0s. So it'd be like having 24 lanes of traffic that could each send 64 cars in a minute. And that would be the equivalent of sending 1,500 cars in a minute. And then we had DS3s, and a DS3 is 28 DS1s. So it would be like having 28 layers of 26 lanes of traffic sending 64 cars in a minute. And that would be 43,000 cars in a minute. So when a company wanted to connect to the internet or connect to the network, it would lease one of these lines, and it would choose based on how much traffic it thought it was going to send, would choose the size line that it wanted to lease. So now we have different protocols. We've got proprietary versus standard. So proprietary is when one company creates the protocol. So in the case of Arpanet, BBN wrote all the code that ran in the computers that ran the Arpanet. They all ran the same code, and they spoke to each other in the way that it was coded, right? They all spoke to each other the same way. There were also standards organizations that were created that we're standardizing how computers talk to each other so that computers from different vendors would be able to talk to each other from different companies. So we see this today. So if you have an Apple AirDrop, you can only you can only send something from one iPhone to another iPhone because Apple AirDrop is a proprietary protocol. You can't use Apple AirDrop to send a packet to an Android phone. It won't work. Just send a file to an Android phone. It won't work. And iMessage is also proprietary. And so you could send something from one iPhone to another iPhone with iMessage, but say your packet isn't going through, you're trying to send a message to one of your friends and it's not going through. You might say, resend this as an SMS text because SMS is a standard protocol. And so that's going to work between iPhones and Androids. So computers speak protocols. They set up a circuit just the same way people do, right? So when one computer wants to talk to another computer, it makes a call request and the other computer gets an incoming call, answers the call, and then the source gets that the call's connected. So say we wanted to send a packet from one computer to the other computer that said, Alice owes Bob $100. The first thing that we do is we convert the message into binary. So this is binary, all ones and zeros, which is what we send down these cables. So Alice, this is A, this is L, I, C, E, this would be space. This would be O, W, E, S, space, B, O, B, space, $100. So that would be how we would convert Alice owes Bob $100 into binary. What we would probably do is split this up and send it as 4 different messages, 4 different packets, and we would number them 1, 2, 3, 4, and we would send them down the line. Now, computer lines, especially in the beginning, we weren't confident at how well they were going to work because noises, like lines are noisy. Telephone lines can be noisy. Just the same way that sometimes you make a telephone call and it's echoey or you hear crackling or something. That's noise on the line. So when computers are talking to each other, they need to make sure that they can still send traffic even in the midst of noisy lines. And so when we would send data, we would send it from one computer to the next computer over the telephone line, and then we would reassemble the packet so that if you sent 4 packets, the destination would make sure that it got 1, 2, 3, 4, and it would tell the source, yes, I got 1, 2, 3, and 4. And then it would reassemble them into the correct order. You need to make sure that the order is correct because if you sent Alice owes Bob $100 and the packets came in the wrong order and you got Bob owes Alice $100, a completely different message, right? So you need to make sure that the packets are coming in the correct order. So the most frequently used applications on early computers were email, which we still use today, and FTP, file transfer protocol, which we also use. You guys use file transfer protocols as well. You're transferring files when you upload a photo to Instagram. So this stuff is still in use now. Now, more companies wanted to get on the network. They wanted to connect together. So say a company had 2 locations. They might lease a DS1 at the 2 sites and connect them together over the phone line. And that would be a private network. So they would connect from location A over the phone network to location B. And now it would be like they were together. They could talk to people in the other location. And computer networks also enabled new applications. Like you could have a bank and you could have different ATM machines. Say you wanted to take money out of this ATM machine. The ATM machine could talk to the bank and say, is it okay if I give this person this much money? And the bank could say yes or no. And then you could get your money from the ATM machine. So there are new applications that are being that we're capable of handling because we have got the telephone network. the computers connected. So poll question, when do you think .com, .org, and .edu were created? 1975, 1985, or 1994? 1985, January 1st, 1985. There were the top level domains .com, .edu, .gov, .mil, and .org created. ARPA was also created, but it was created as a temporary top level domain. Now we've got lots of them. We've got .ca for Canada, .conz for New Zealand, .biz, .me. But in the beginning, so 35 years ago, there were these 5 created. So now more and more companies and schools and such are getting on the network, and the telephone companies are saying, we can't run all of these data over our telephone network. This is nuts. So they created optical networks. So there was an optical transport of sonnet rings. So optical fibers were much faster. OC1 would run 52,000 cars, the equivalent of 52,000 cars in a minute. And OC192 would run the equivalent of about 10 million cars in a minute. So they're much faster. They also connected the networks together in rings. So, you know, I live in Massachusetts, we've got a ring 128 around Boston, and there are rings around lots of cities. So the phone companies created rings of computers and connected the rings together. Now, the reason that they made rings is if you wanted to talk from this computer to that computer, you could just send the traffic. But say this link went down, you'd still talk to that computer by just going around the ring. And so there was more resiliency by creating rings. So there were 3 changes made in the network to accommodate the higher scale of having all these new people and all this new traffic on the data on the network. First, faster WAN protocols were created that had more connectivity options. So now we created networks that weren't so heavy. They didn't have to do so many things to set up a connection. And also what they let you do is, instead of only being able to create a private connection across the network, you could now talk from this location to multiple locations. So you could connect from your company site A to your company site B. You could connect to a different company, company C, or you could connect to the internet and do lots of things off the internet. So these new WAN protocols offered more connectivity options. We also ran Internet Protocol, IP, and routers were advertising routes. So when a company got like a .com or a .edu address or something, it also got a network number, a network ID, just the same way that we have in the telephone network, we have a country code, an area code, and exchange. Companies would get a network ID, and they would tell the router what their network ID is, and the router would advertise that to the other routers in the network. Say if you want to get to network 5, come to me, send the traffic to me. And if you want to get to network 183.33, come to me. I support that network. So each of the routers would say what networks they supported, and they would tell the other routers, and they would be able to discover the way to get to that address through the network. So instead of setting up circuits, they would just send traffic to where it was going to go unidirectionally, packet by packet. So that when you made a phone call, you owned all of the resources. But if you sent a packet one at a time, then you could just send that without having to set up a circuit and reserve bandwidth for a particular connection. The other thing that happened is that we moved resilience to the ends of the network. So before I told you that we would send a bunch of packets and we would reassemble them, and then we would send them again and reassemble them. We stopped doing that. What we started doing was sending the packets through the network and reassembling them at the destination. So if the source sent packets 1, 2, 3, and 4 to the destination would say, I got up to 4. And then the source would send 5, 6, 7, and 8 and say the destination just got 5, 6, and 8. It would say, I didn't get 7. And so it would resend 7 through the network. So we've moved the resiliency out of the middle of the network and to the end of the network. I told you when we had the computers connected through the Ethernet switch that I would tell you what happens when a link is overwhelmed, when it has too much data traffic. What happens in a network is if there's too much traffic in the network starts to just randomly throw away packets. So if this computer sent 1, 2, 3, 4, 5, 6, 7, 8 to this computer, and this computer said, oh, I didn't get 7, then the source thinks, ooh, the network is probably busy. I need to slow down how much traffic I'm sending it. I need to send the data more slowly. And so that's what it does. It backs off and sends the data more slowly so that there's not as much congestion in the network. So that's how we tell computers to stop sending as much traffic. We just start randomly throwing away packets. And then in that way, they know it's time to slow down. So now, in addition to having computers connect to the network, now people in their homes wanted to connect to the network. So when I was a kid, TV was free. So we had like 5 TV channels. We had ABC, CBS, NBC, and then a couple of local channels. And that would just come to your house. But what the cable companies wanted to do was have premium channels, sort of like the way we have like Hulu and Disney Plus now. But what they did is they bundled together a whole bunch of premium channels like ESPN and CNN and TBS. And so they bundled together a whole bunch of different channels, and then they sold those as packages to people in their houses. What they did was they connected the houses with these coax cables. And so they used these cables to send down these TV channels that you had to pay for. And then eventually started using this for internet as well. And then Verizon started selling Fios, where they were bringing optical channels to the house. And they were running 3 wavelengths on the channels, on the fiber to the house. One was for sending voice and data calls to the house. One was for sending voice and data traffic from the house into the network, and one was sending TV channels from the network to the house. So now we've got neighborhoods that are connected to the network as well as companies. And this is the access part of the network. This is the edge of the network where people are accessing the network. And then when this neighborhood and this neighborhood are connecting, their traffic is being aggregated at this device. This device is aggregating traffic from lots of different places and sending it forward. Now, all of these houses are sharing this link right here. So that means if someone in this house is using a lot of data, if they're downloading 2 or 3 movies or something, they're affecting the capabilities of this house because we're sharing this link here. And then if someone in this neighborhood is doing something, they can affect what's going on in this neighborhood because they're sharing these links here. So traffic is being aggregated and you're able to affect traffic because you're sharing the same links. So now we've got more and more people on the network, more and more data going through the network. So even Sonnet wasn't fast enough. So we started deploying optical fibers in the service provider's network. And optical fibers could have up to 96 wavelengths running on the single fiber. And those wavelengths could carry a certain amount of data. So the company that I work for has optical fibers that support wavelengths that can send up to 800 gigabits of data per second. So in our relative car analogy, that would be like sending 800 million cars in a minute. so it's very fast. And they can support 48 800 gigabit wavelengths on a single fiber, on a single strand of fiber. And so that's the equivalent of sending 38 billion cars in a minute. So now we can support lots and lots of traffic. And so there's a lot of fiber connections in the world now where we're sending lots of data through the network. These fiber connections are really in the core of the network. So at the axis, we're sending less and less traffic. And as we get closer to the core of the network, we have more traffic being aggregated together. So another poll question. If it takes less than a second to download an HD Harry Potter movie on an 800 gig wavelength, how long do you think it would take to download the same movie on a DS0 telephone line? 12 minutes, 12 hours, 24 hours, or 275 hours? So it's 275 hours. So you'd probably be better off reading the book. So now computer networks are very fast and everyone's connected. So we should be done with these networks, right? No. So first, because everyone uses Ethernet protocols on their LANs, we wanted to move Ethernet into the WAN. But it needed to have better scale and better resiliency. So we created carrier Ethernet. And then people didn't want to have to plug their laptops directly into their router. So we created Wi-Fi networks. So in a Wi-Fi network, your laptop talks to your router over a radio network. And we also have Bluetooth networks where you speak from your AirPods to your phone or from your watch to your phone using Bluetooth radio technology. So it's a different technology, a different network. And then people wanted to be able to use their telephones for email as well as talking. So we have 4G mobile networks. And they were the first mobile networks that were digital, where everything was digitally encoded. And now we have 5G networks. We're starting to deploy 5G networks. And 5G networks have much more scale. They scale in 3 directions. They support more devices because now we're going to have more things connected to the network with the Internet of Things. So we'll have people and devices connected to the network. So, and we scale how much bandwidth you can use so that you can get a lot more bandwidth on your phone. You can do more things on your phone faster. And we also have better latency. So there's less delay in sending information across the network. So you think, well, when we have all that done, we should be done, right? No. Because once everyone was connected to the network, now there was new content on the network, right? There was a way to bring new applications to the people who were connected to the network. So the World Wide Web started to be used in 1994, and companies could now start advertising on the network, and they could start selling products on the network. The Google search engine was used in 1999. You could look and find something that you were looking for on the web, find where it was. Facebook started its social network in 2004. You could start connecting with your friends. Amazon was selling things in 1995. Netflix started streaming movies in 2007. So prior to that, if you wanted to rent a movie from Netflix, they would mail you a DVD. You would watch it and mail it back. But in 2007, they could start sending you your movies over the computer network. Fortnite was released in 2017, and Zoom has become very important to us during the coronavirus pandemic. So all these applications were made possible by the fact that we have computer networks. So these applications exist in the cloud, and the cloud is really data center. Some people say the cloud is other people's computers, but it's basically computers in a different location. And the computers have CPU, which is the brains that does the work. It's got memory, how much it can remember at one time, how much it can do at one time, and it's got data storage. So if I were to ask you a question and you just knew the answer, it was in your memory. But say you couldn't remember the answer, but you knew where to go look it up and you went and looked it up. That would be like using data storage. And then we also have connectivity in these data centers. They're all connected together. The computers in the data center are connected together, and the data centers are connected together, and then the data centers are connected to the user. So like if Fortnite was running in this rack and you were playing it, you would connect into this data center and run Fortnite in a server in this rack. So what does the Fortnite server network look like? Well, in May 2019, this is what it looked like. So now, say you live in Washington, D.C., and you were playing Fortnite with your friend that lived in Miami. You'd have a little bit of an advantage because you guys would be using the Fortnite server that's in Virginia. So you're closer to it. So you might have a little bit of an advantage because anything you typed would get to the server faster than whatever your friend typed. So when we look at the Fortnite network, you're thinking about latency, how long it takes something you type to get to your destination. As network architects, we think about latency. So latency is also called delay. We think about latency, and we also think about throughput, which is how much bandwidth can go on the links, how much traffic can be forwarded through the network. Just like if you were driving in a car, how many cars can go down the highway? We also think about jitter, which is the variation in delay of a packet. So if all packets have the same delay, that's okay. You can deal with that. As a human, you can deal with that. But say I started talking really fast and then I started talking really slowly. That would be very annoying to you because you want the delay to be the same between all the different words. And imagine if you were using your mouse and it was going really slow and really fast, you wouldn't be able to depend on what was going to happen. So jitter is something we have to worry about in the network. We don't want there to be a lot of variation in how long it takes the packets to come through. And then we worry about priority. We want the most important packets to go through first, or go through. If there's too much data in the network, we want to make sure that we throw away less important packets, not more important packets. So you guys see this if you use FaceTime, right? If you're talking to someone on FaceTime and your connection is bad, the video will pause. It'll say connection is bad, I'm pausing the video, but you'll still be able to hear them. You'll still be able to hear your friend. You'll still be able to talk to your friend because the voice traffic is more important. So it goes through and we stop the video traffic because it's less important. And we do that for lots of different traffic in the network. We know which traffic is more important and which traffic is less important. And that's how it's prioritized through the network. Now, the next thing is, so now we've got these content providers, right? And they want to use the network too. So when they first started using the network, they would also buy a connection from the service provider. And say we had Netflix and they were connected into your service provider and you wanted to watch the green movie. And so Netflix would start sending you the green movie. And then this house wanted to watch the blue movie. This house wanted to watch the red movie, and this house wanted to watch the purple movie. So all of this traffic is being sent over the service provider's network. So this is a lot of traffic being sent over the service provider's network. And this isn't good for the service provider, and this isn't really good for Netflix either. So the service provider is saying, look, I built my networks. These are pretty expensive to build, and you're running all of your traffic over my network. That's not really fair. And Netflix didn't really like it because if you were watching a movie and there was too much traffic over the service provider's network, packets would get thrown away and your movie would be choppy, or it might stop in the middle. I mean, it wouldn't be a very good experience for you either. And so what the content providers did is they started building their own networks. So if you wanted to watch if we still wanted to watch the same movies, what Netflix would do is they would access the service provider's network, but much closer to where you were. They would try to be at the edge of the service provider's network, so that if you all asked for the movie, it only had to go through a very small portion of the service provider's network. And instead, Netflix would use its own network to download the movies. And these are probably very fast connections, like the 800 gigabit per second connections, right? The optical connections that we support. So say all of you guys are asking to watch the same movies. This Netflix server would ask the main Netflix server, can you send me the 4 movies? And say they each took a second to download. So now this server has got all of the movies over its own network. It's not going through the service provider's network, and you guys are getting much better experience watching the movie. And the service provider is happy because now their network isn't being used up for Netflix traffic, because it's not just Netflix, it's Hulu and Disney Plus and everyone else, right? They're all going over the service provider's network. So now they all have their own networks, and they're trying to get access closer to where the people who are buying the service live. So the internet is a combination of different networks, right? There's lots of different networks. Just the same way as if you were in your house in New York and you wanted to go to a location in California, you might walk to the bus, take the bus to the train, take the train to the airport, fly to California, rent a car, and drive to the house that you're going to. So these are all different transportation networks, right? Walking isn't really a network, but the bus is a network, the train is a network, the plane is a network. Say on your way back, your car broke down and the rental company said, oh, we'll come and get it. Maybe you took an Uber to the airport. You couldn't get a direct flight, so you flew through Chicago and then you flew to New York. You got on the train, you took the bus, you walked home. So this is a bunch of different networks. It's the same on the computer network. So say you're at your house, you connect to your Wi-Fi network, you go up to the computer that's aggregating the data, that's giving you access. It's being aggregated over a 10 gig link to an outdoor router. It's getting aggregated again over 100 gig links. So as we get to the center of the network, the link speeds are going up because more and more people are connecting over these same links. And then say you're talking to your friend who's on his cell phone in California, and say he's driving down the road. He might be connecting to one cell tower and then the next cell tower and then the next cell tower. And he's connecting over a radio network to the cell towers, and this is all being backhauled to him. So again, you've got a network of networks, and they're slower at the outside and they get much faster in the core of the network. And then they slow down again as they get to the destination. So what devices are on the network at your house? So you've got your laptop, your phone, maybe you've got some tablets, you've got your cable modem, your router, smart TV, printer, Alexa, you've got maybe a Nest, some smart lights, a webcam, your games, TiVo. There's so many devices on the network now, your phone. And so now there's so much connectivity and we're using it for everything. It's pretty amazing what the network has enabled to be created. So I just want to talk about one more thing before we finish. When I started working on networking, the first thing I worked on was network management. And network management is the computer that controls the computers that forward the traffic in the network. And it sets up connections in the network. It monitors the network. The computers have sensors with information in it, just the way that your car has got sensors. So you might have like a sensor that says the check engine light is on or your tire needs air. So what network management does is it checks all the computers to see if there's any indications that there might be a problem in the network so that we can fix the problem before it breaks down, just the same way that you want to do with your car. So when we first started doing network management, we really a vendor managed only their own devices. So the same way as if you had a Toyota, you would go to the Toyota dealer, or a Honda, you'd go to the Honda dealer. Juniper would only monitor Juniper devices. Nokia would only monitor Nokia devices. Ciena would only monitor Ciena devices. But now that the network's getting so big and there are so many different applications and so many vendors in the network, we want to be able to monitor and manage multiple vendors' equipment from one location. And we also want to start automating things so that things happen automatically, because now the network is getting so big that it's much easier to check things and have the computer do things that people used to do. And so it's a pretty exciting time in network management to start automating and managing these computer networks. So it's a pretty cool thing. So we've come a long way. Let's see, I'm gonna have a hard time finding. So basically these are two videos. The one is computer operators. So originally, when you would make a phone call, there would be a telephone operator that would connect the two houses together so that you could make the phone call. And now we're on FaceTime, where even a little kid can FaceTime their grandparents. And it's pretty amazing how far we've come in really not that long a period of time. So how many computer networks do you think you use now? It's definitely way more than 5. So thanks for watching the video. I hope you learned something and I hope you enjoyed this. Take care.